Did you know that the oceans have absorbed over 90% of the extra heat caused by human activity since industrialization? Think about that for a second. The vast, vast majority of the warming we've caused is actually hidden beneath the waves. Today, we're diving deep into a really fascinating set of sources one of you shared to unpack the dramatic changes happening in our oceans and what they mean for sea levels.
Exactly. And this deep dive, it's going to take us through some critical shifts. Ocean temperature, salinity, the way the water layers form, stratification, also increasing acidity, and the growing threat of marine heat waves. And then, yeah, we'll definitely tackle the crucial issue of sea level rise. Our main source is the IPCC's latest big report, the Sixth Assessment, AR6. But we've also got a range of other insightful scientific articles offering different perspectives, zooming in on specific things.
Okay, right. So let's lay out what we've got here. We'll be looking at an analysis of that IPCC AR6 report from Elmsjön, which gives us that, crucial big picture. Then we've got this really interesting piece from Science News. Apparently, an Antarctic glacier is refreezing its cracks, which sounds, well, surprising, a real curveball.
Definitely stands out.
And we're also going to look at an article from a site called Science Under Attack. It presents a, let's say, contrarian viewpoint, questioning this idea of accelerating sea level rise. It's really vital we explore these different angles, right, to get a fuller picture.
Absolutely. Couldn't agree more. And to round things out, we have a study from the Journal of Glaciology focusing on snowmelt refreezing up in the Himalayas. It gives us a key regional look at the cryosphere. We'll also touch on related climate articles from Yo and Egasan, a blog post from Hame giving some historical context on past sea level changes, ups and downs. And of course, a key excerpt directly from the IPCC report itself on ocean climate change and sea level. It's quite a mix.
It is. So your mission, should you choose to accept it, is basically to absorb the most critical insights from all these varied sources about ocean changes and sea level rise. We want to bring you the surprising facts and hopefully a clear overview of what's happening without leaving you feeling, completely swamped by information, ready to take the plunge.
Let's dive right in. Starting with ocean temperature makes sense. The IPCC AR6 report, as analyzed by Sangil Koyen, really hammers home this immense role the ocean has played, soaking up the heat from our emissions. Over 90%, it's just a mind-boggling amount of energy.
It really is. And here's where it gets really interesting, I thought. The rate the ocean is heating up, it's faster than almost any point since the end of the last ice age.
Yeah.
The only comparable period of rapid warming was something called the Younger Dryas, way, way back around 120,000 years ago. The fact that our current warming rate matches that ancient, really rapid shift, well, that should grab our attention, shouldn't it?
It certainly should. And these latest IPCC findings, they really reinforce what previous reports like AR5 and the SROCC have shown about this continuous increase in ocean heat content since industrialization. But the warming isn't happening evenly. The top 700 meters or so of the ocean, that's warming the quickest.
Right. Why is that?
Well, it's mainly because the deeper waters mix much more slowly. Think of it like trying to stir a really deep pot. The top heats up first.
Okay, that makes sense. So the upper layers are the most exposed. They're responding fastest to the heat going in.
Exactly. And as you go deeper, our confidence in the warming trend, well, it naturally decreases a bit. The report says it's virtually certain in that top 700 meters.
Yeah.
Then very likely between 700 and 2,000 meters, and likely below that. We've also seen this really consistent climb in the global average sea surface temperature, the SST, throughout the 20th century.
And those surface temperatures have really taken off in recent decades, haven't they? I remember seeing charts on that.
They absolutely have. Yeah. The average SST between 2011 and 2020 was nearly a whole degree Celsius higher, 0.88 degrees C, than the average between 1850 and 1900.
Yeah.
And get this, a massive two-thirds of that increase has occurred just since 1980.
Wow. Since 1980.
Yeah. Looking ahead, the IPCC projections for SST increases by the end of this century. They're quite stark. They range from about 0.86 degrees C and a lower emissions future, that's the SSP1 2.6 scenario,
Okay.
up to a potentially dramatic 2.89 degrees C increase under the high emissions SSP5 8.5 scenario.
Okay.
And some extreme scenarios looking further out to 2300 even suggest rises of up to 10 degrees C in certain ocean areas.
10 degrees Celsius surface temperature rise. The implications for marine life are just terrifying to think about. Okay, let's shift gears a bit. Let's move on to ocean stratification and salinity. What key changes are we seeing there? How the layers are forming, the saltiness?
Right, so the AR6 report highlights that our observations of ocean salinity, how salty the water is, have improved quite a bit. And what's particularly interesting is this pattern. Areas that were already salty have generally become even saltier. And areas that had lower salinity, fresher water have tended to become even fresher. And this pattern holds since around 1950.
So it's like an amplification. The existing patterns are becoming more extreme. Salty gets saltier, fresh gets fresher.
Precisely. And this surface warming we talked about, it isn't uniform across the globe either. The Indian Ocean and the area around the Gulf Stream seem to be warming fastest at the surface.
Okay.
But even with those regional differences, the report states it's very likely that at least 83% of the total ocean surface will warm throughout the 21st century under all the emission scenarios they looked at. And this surface warming directly impacts ocean stratification. It makes the layers more stable.
More stable. How does that work?
Because warmer water is less dense, right? So it tends to sit on top of the colder, denser water below, and it resists mixing, like oil and water, as you said earlier.
Right. Got it.
And the data shows this stratification, this layering, increased by a significant 4.9% just between 1970 and 2018. That's actually double the previous estimate.
Double. Wow.
Yeah. And the report is virtually certain that this upper ocean stratification will just keep increasing during this century. What's kind of fascinating or worrying here is that this stronger layering acts almost like a lid on the ocean. It hinders the vertical exchange of water between the surface and the deep.
And why is that a problem? What does that affect?
Well, this reduced mixing can disrupt large-scale ocean circulation patterns. It can also limit the ocean's ability to absorb vital gases from the atmosphere, like oxygen. This could potentially create or expand these oxygen-depleted zones, which are really tough for marine life.
Okay, that makes sense. Reduced mixing has big knock-on effects.
Definitely. Now, let's talk about a direct consequence of the ocean absorbing all that CO2 we release, ocean acidification. What's the latest understanding there?
Right, the other CO2 problem, as they sometimes call it.
Exactly. The ocean acts as a major sink for the carbon dioxide we pump out, and this absorption leads to a decrease in the ocean's pH. That's acidification. The AR6 report uses what they call proxy data, things like the chemistry found in ancient shells to figure out past ocean conditions. And they compare our current situation to a period called the Paleocene-Eocene thermal maximum, or PTM. This was a time of rapid warming about 56 million years ago.
Wow, okay, 56 million years ago.
Oh.
That gives us some serious deep time perspective. What did they find in that comparison?
Well, interestingly, the estimated amount of acidification back then during the PTM is actually similar to what's projected by the end of this century under a high emission scenario, about a 0.4 pH unit decrease.
Similar amount, okay.
And this is the crucial difference, the acidification during the PTM happened over thousands of years. We're seeing a potentially comparable change happening within a single century. The speed of this change is what's really unprecedented and concerning for marine ecosystems.
Ah, right. So it's not just the level of acidification, but the incredibly rapid pace it's happening at now. Organisms don't have time to adapt.
Precisely. The report also looked into what happens if we were somehow able to actively remove CO2 from the atmosphere. And while that could relatively quickly help the surface ocean acidification, the deep ocean is a different story because of that slow mixing we keep mentioning.
It takes ages for the surface changes to reach the deep.
Exactly. The deep ocean will continue to accumulate carbon and remain acidified for centuries. So the impacts, especially deep down, are essentially irreversible on human timescales, decades to centuries, even with aggressive CO2 removal.
That's a really stark reminder, isn't it? The long-term commitment we're making with our current emissions. Okay, let's turn our attention now to marine heat waves. These seem to be making headlines more and more often. What did our sources say about these extreme events?
Yeah, marine heat waves, basically prolonged periods of unusually warm ocean temperatures, are definitely becoming more frequent and intense because of climate change. The IPCC report notes that the frequency of these heat waves has roughly doubled since the 1980s.
Double in just a few decades. That's a really significant increase.
It is, and they're not just happening more often. The report says they're also lasting longer and becoming more intense when they do happen. In fact, it highlights that the most impactful marine heat waves, the really damaging ones, have become over 20 times more frequent in recent decades. And that increase is attributed to human-caused global warming.
20 times more frequent. That really underscores the human fingerprint on what's happening in the oceans. What do the future projections look like for these?
Not great, unfortunately. Yeah. By the end of this century, these extreme events are projected to occur about 4 times more often under a lower emissions scenario, and a staggering 8 times more often under a high emissions scenario.
8 times more often.
Yeah. And these heat waves, as we know, can have devastating impacts on marine ecosystems. Think coral bleaching, widespread fish die-offs, impacts on marine mammals, fisheries, the whole food webs.
Absolutely. We've all seen those heartbreaking images, unfortunately. Now, shifting focus to a very specific region, that Science News article you mentioned brought up something quite unexpected in Antarctica, this refreezing of cracks in a glacier. Tell us more about the Cam ice stream.
Yeah, this is a really interesting counterpoint almost to a lot of the concerning news we hear from West Antarctica, which is generally experiencing rapid ice loss. Researchers studying the Cam ice stream, which has actually been pretty stable compared to its neighbors, discovered evidence of refreezing happening within these massive cracks, called basal crevasses, on the underside of the ice.
Refreezing within the cracks. How on earth does that work?
Well, it appears that these greenish-looking blobs of refrozen ice are forming. They're made from a supercooled mixture of seawater and meltwater. And this refrozen ice seems to be filling these huge crevasses from the top down, potentially sort of healing these cracks over many decades.